Hello, everyone. My name is Chenxi, a fifth-year PhD student of Institute of Computing Technology, Chinese Academic of Sciences. Today, I will give a presentation for our work, Beehive, a scalable disaggregated memory runtime exploiting asynchrony of multithreaded programs. Memory plays an important role in data centers. Recent years have seen rapid growth in memory demand, increasing its share of total cost. However, low server memory utilization leads to significant resource waste. Memory disaggregation system has been developed to address this issue. Compute servers with small local memory are connected to remote memory pools via high-speed networks. Size of memory allocated in the remote memory pools is dynamically reconfigurable, achieving high resource scalability and utilization. But there is a gap between local and remote memory. Accessing local memory takes only 60 nanoseconds, while accessing data on remote memory requires several microseconds. The state-of-the-art solution involves managing remote memory with a runtime system. Data is managed in object granularity with remoteable pointers to alleviate I/O amplification and utilize the program semantics to improve the prefetching effectiveness. Okay, when the application accesses an object in remote memory, it dereferences a remoteable pointer. The runtime issues a network request, and the application must wait for several microseconds to receive the data, and this is a waste of CPU time. To improve CPU utilization, the state-of-the-art system, AIFM, switches thread after issuing a remote accessing request. By using user-level threads, only about 50 nanoseconds is cost for context switching, and this achieves high CPU utilization. But at what cost? Here, let me present an experiment conducted on a multi-grid PDE application upon two state-of-the-art systems, Huimin and AIFM. We compared two memory configurations, placing all data in local memory versus configuring local memory to hold only 13% of the data, with the remaining data stored in remote memory. Huimin is developed based on Linux paging and swap system. It is transparent for applications. It manages data at the page granularity. We can see that over 75% of the CPU time is spent in kernel space because of page table management, swap entry allocation, and other kernel space overhead. On the other hand, AIFM, the runtime-based system which bypasses the kernel, also shows significant application slowdown. One reason is the scheduling overhead, because each access to remote memory triggers a thread switch. Meanwhile, thread switching disrupts data locality, leading to a 6.5 times last level cache misses, and significantly slowing down the application. By mitigating the microsecond scale latency through thread switching, high CPU utilization is achieved, but this approach decreases CPU efficiency. So the question is, can the application generate enough concurrent remote memory accesses to mitigate the microsecond latency and also provide good data locality to avoid excessive cache misses? And the answer is yes. Here is our major insights. First, let a thread run to completion can maintain well-organized data locality. And second, computation in one thread without data dependency can execute asynchronously to exploit high CPU efficiency and remote access concurrency. Consider the code on the right. Two objects in remote memory are references by two remotable pointers, PA and PB. We need to dereference the two pointers and perform calculation with function foo and bar. After dereferencing pointer PA, we need to wait for the network response. However, if the calculation of foo and bar have no data dependency, we can move the computation of bar forward to overlap the network transmission, like this. So can we automatically generate such high-performance asynchronous execution code? There are two challenges. The first challenge is how to transform synchronous code to asynchronous code automatically. The key problem is pointer aliasing. It introduces hidden data dependencies, and that is difficult to detect through static analysis. But this pointer aliasing problem can be solved with ownership tag. In the Rust programming language, an object can have either one mutable reference or any number of immutable references. So possible aliases such as RA and RB in the figure must be immutable. Since the reference data is read-only, there is no data dependency between foo RA and bar RB. On the other hand, RC is a mutable reference, so it should not have any aliases. There is no data dependency between bar RB and baz RC, since they operate on different objects. In Beehive, developers can annotate code involving remote memory access as pararoutine. A pararoutine is an asynchronous computation unit we propose, derived from Stackler's coroutine. The Beehive compiler can then automatically analyze dependencies between pararoutines and generate asynchronous code. And the second challenge is how to efficiently mitigate microsecond scale remote memory access latency. So we developed a lightweight and efficient cooperative scheduler for pararoutines. During the code execution, the runtime will sequentially launch the pararoutines as in the left. As shown in the figure, the pararoutine foo is launched, and the runtime will allocate a frame for it from a dedicated thread local pool, which is very fast. After which, the execution of this pararoutine begins. Once a remote access occurs, the pararoutine suspends and its continuation is enqueued into the waiting queue. The next pararoutine is then launched. So if the size of a waiting queue reaches the threshold, the scheduler checks whether the network request of the front mode pararoutine is completed, and if so, it will dequeue the continuation and resume the pararoutine. Overhead for launch or switch a pararoutine is as low as 10 nanoseconds because it is lockless and it introduces no inter-thread communication. And it enables Beehive to efficiently mitigate microsecond scale latency. We have evaluated Beehive on 8 workloads using a range of local memory ratios. The baseline includes AI-FM, which is the state-of-the-art runtime system, and the paging-based system Hermit and FastSwap. We can achieve a much better throughput rather than our baselines, and on average, Beehive performs 1.58 times better than AI-FM. Let's take data frame taxi as an example. Data in this application is organized as some 2D tables in memory. The application performs a series of filter, range, and group by operations. For load balancing and high parallelism, data is sliced and evenly assigned to different threads. Therefore, a thread switch will change the working size of current processor core and cause a large number of cache misses. Beehive can reduce the thread switches and outperform AI-FM by 1.54 times because it reduces the last level cache misses and the scheduling overhead. And also, Beehive can achieve better tail latency. For example, in the social network application, it gets a better P90 tail latency because of a good CPU efficiency. It reduces large level cache misses and scheduling overhead. Finally, here is some key takeaways. Thread switching is not optimal for mitigate microsecond scale latency because of a poor data locality and non-trivial scheduling overhead. Beehive achieves high CPU efficiency and high concurrency through asynchronous execution in one thread. We exploit concurrency through types and compilers, and we mitigate microsecond scale latency via lightweight pararoutine runtime. Beehive is open source on GitHub, and thank you.